In this module, we will learn about kinematics. Kinematics describes the motion of objects. We will not go into details about the origin of such motion. We will just assume in this section that the object is already in motion, and we will analyze what is needed to describe that motion. Later on in the modules involving forces and Newton's law, we will go through the origin, the source of such motion, the cause of motion, the causes of motion. And so to describe kinematics, we will obtain some physical quantities, some variables that will help us to describe the motion and also predict the motion at some future instant of time. And we will look into two special cases of motion, motion with constant acceleration in one dimensions, and the other case that we will analyze is projectile motion, which is motion in two dimensions. So the first quantity that we will describe is the position. So in order to describe the motion of an object, we need to describe the position of an object. We will also define two other quantities, velocity and acceleration. But first, let us deal with position. So to describe the position of an object, we need a reference frame or a coordinate system. We also need an origin because we need to point out the location of the object relative to the origin. So a position in three dimensions is described by a vector such as r equals rx times I plus ry times j plus rj times k. Here I, j and k are the unit vectors pointing along each of the Cartesian axis, as you have learned in the module on vectors. So this simply means that the object's position is rx units along the x direction, ry unit along the y direction, and rz units along the k direction. Now, it's important to trace out the path of an object and to describe such paths, and this is given by the position time graph. For example, at a time instant t1, an object can be at location r1, at position r1, and at some other time in the future, at t2, the particle could have moved to another position r2. So we can refer these positions r1 and r2 as you see in the plot here in a three-dimensional coordinate system, and the actual path could be very complicated. To go from r1 and r2, the particle need not travel in a straight line, but can have a very complicated path, as you can see in this plot. And so we will obtain the quantities that describe such motion in more detail. So the first quantity we will look at is called displacement. It's defined as the difference between the final and the initial positions. In this case, it's just r2 minus r1, and remember r2 and r1 are vectors, so you have to subtract them with rules of vector addition and subtraction. And the time difference delta t is t2 minus t1. So we have the displacement. Displacement is a vector quantity delta r, and defined as some final position minus some initial position r2 minus r1. And the displacement is a vector quantity, and it has the unit of meters. You can compare it with the distance traveled by the object. Distance is a scalar quantity. It also has the units of meter, but it doesn't have a direction associated with it. For example, in this curve, the distance is the total distance traveled in this complicated path between r1 and r2, but the displacement just depends on the final position and the initial position. So it is the straight line distance in this case between r2 and r1 as seen in this graph. Then this takes us to our next variable, the velocity. In this case, we will define the average velocity first. So average velocity is defined as displacement over some time interval. So in this case, delta r over delta t. And remember, delta t is a scalar, but delta r is a vector. So average velocity also is a vector. Its unit is meter per second. And then we have another quantity that tells us if the velocity is changing over time or not. And this is called acceleration. In this case, we define an average acceleration as change in velocity over change in time. So some velocity interval delta v over some time interval in which that change in velocity took place. And as you can see, acceleration is also a vector quantity. And from this equation here, you see that it has the units of meter per second square. So let us now distinguish between instantaneous and average quantities. So far, the velocity and the acceleration we have described are average quantities, but we also need to know the velocity of a particle at a point in time and also its acceleration at a point in time. So let us go through this example. Over here we show another position time graph, but this is for one-dimensional motion along x direction. So the horizontal axis represents time and the vertical axis the x position of the particle. And let us look at 2 points points in time, t1 and t2. At these 2 points, the particle has positions x2 and x1, and so the average velocity, as before, we can define as x2 minus x1 over time interval t2 minus t1. But we also want to know the instantaneous velocity, and you can see the path is quite complicated from t1 to t2, but we want to know the velocity at t1 at time t1 and also the velocity at time t2. And this is given by the tangent to the curve at these points t1 and t2. The tangent represents the instantaneous velocities in this case. And we can also relate this to calculus derivatives, because the average velocity is given by the change in displacement over change in time. And so we have to, for instance, to calculate instantaneous values, we have to take the limit where the time interval goes to 0. So this delta x over delta t, as delta t goes to 0, becomes dx over dt, which is just the derivative of the position time graph. So the instantaneous velocity is given by the derivative of the position time graph dx over dt. And the instantaneous acceleration is also defined in the similar limit. The average acceleration is defined as delta v over delta t, change in velocity over some time interval delta t. And if we take the limit as delta t goes to 0, we see that this approaches the derivative dv over dt, which is the time derivative of the velocity. So instantaneous acceleration is just given by the time derivative of the velocity. And if we use the definition of instantaneous velocity we just derived, so we see that this is actually, acceleration is related to the second derivative of the position with respect to time. So this is, acceleration is given as d2x over dt2. That is the second derivative of position over time. So if we know the position over position time graph, we can calculate both the instantaneous velocities and the instantaneous acceleration. Now let us look at some example. First, a case of constant velocity. So you see a car traveling at constant velocity represented by these vector arrows, and notice that the arrows are of same length. They don't change in size. That means the velocity is constant. So when the velocity is constant, what is the acceleration? So acceleration is given by change in velocity over change in time, and the velocity is not changing over time in this case. So the acceleration is equal to 0 in this case. Now let us look at a case where there is a positive acceleration. So you again see a car, and its velocity is represented by the black arrows, and you can see the black arrows are increasing in length over time, and the red arrows represent the acceleration. In this case we assume that the acceleration is constant, so the red arrows have constant length over time. So why is the acceleration positive in this case? Because the final velocity is greater than the initial velocity, so that delta v gives us a positive quantity, and delta t time is always positive. So the average acceleration delta v over delta t is positive in this case. So the acceleration is positive. Now let us look at a case of deceleration where the car is slowing down over time. So again, the initial velocity is large, drawn by a large arrow, and as time progresses, the length of the arrow decreases, which means the velocity is decreasing. And we also assume this is a constant acceleration case. So we see the length of the arrow, the red arrow that represents acceleration, is constant, but it's pointing in the other direction. That means it was positive before, now it's negative. And this makes sense from the definition also, that the average acceleration is delta v over delta t. Now the final velocity is actually smaller than the initial velocity, right? So v2 minus v1 gives us a negative quantity, and time is always positive, so the acceleration is actually negative in this case. So this is called deceleration, and as you see, as a result of the deceleration, the car is slowing down. So in general, when an object's velocity and acceleration are in the same direction, the object is speeding up, and when the velocity and acceleration are in the opposite direction, then the object is slowing down. Now we will describe some equations of motion that will help us to find relations between position, velocity, and acceleration as a function of time. And the case we will be looking at is a special case, but a very important case. It's the case when we assume that the acceleration is constant over time. The acceleration is not changing over time. And this is represented by this curve, A versus t, A as a function of t. And we see the curve is a horizontal line. So this means over time, the acceleration is constant. The slope of the curve is 0 in this case. And remember, we defined acceleration as the time rate of change of velocity. So the velocity is actually a linear curve, as you see here. If you plot velocity over time, it gives you a straight line at t equal to 0. It is starting in this curve. It is starting at vx0, and it's changing over as time progresses. It's that velocity is changing, but the slope of the curve is remaining the same because the slope gives you the acceleration. Now we will go into the details of these equations and see how to derive them. So this case of motion, the 1D motion, it's primarily given by 3 equations, and you see the 3 equations here in the slide. We assume that it is 1D motion, and we assume that the acceleration is constant. So the first equation gives you the position of the particle, assuming that the particle starts at an initial position x0. It has some initial velocity vx0, and it has traveled for some time t. Then this equation, x equals x0 plus vx0 times t plus half times ax times t square. So this gives you the position of the particle at some time t. And if you want to know the final velocity of the particle, then there is this other equation, the second equation, Vx equals Vx0 plus Axt. So notice this doesn't have the variable x. But if you happen to know the initial velocity of the particle, Vx0, and its acceleration, and if you are given the time t, then you can find the final velocity of the particle. There is another equation that can be derived from these 2 other equations. It's Vx squared equals Vx0 squared plus 2ax times x minus x0. That is the displacement. And to solve problems, you have to pick which equation to apply. For example, if you are not given the final velocity of the particle, you can work, but you are asked to find the position of the particle, you can work with the first equation, x, because you don't need vx in that case. And if all the other variables are given, you can obtain the value of x, the final position. So if the problem doesn't mention the position, but the problem is asking you, for example, about final velocity or initial velocity or acceleration, given some other quantities, then you could apply the second equation. And notice in the third equation, the time variable is missing. So the problem doesn't actually tell you the time. You could apply the third equation. So it just depends on the scenario described in the problem that you have to pick which equation to apply to solve a problem. Now let us derive two of the basic equations we have just talked about. And the first one comes straight from the definition of acceleration in terms of velocity. So because we have assumed the acceleration to be constant, it is not changing over time. So the average acceleration is also equal to this constant acceleration. And from the definition of acceleration, we see that it is the change in velocity over some time interval. So we assume that the particle was traveling with velocity v naught at some time instant t equal to 0, and after traveling a time t, the particle has assumed some final velocity v. Then we see the average acceleration is given by v minus v naught over t. And then we need to find the final velocity. So we rearrange this expression and we get one of the equations we have just talked about. V equals v naught plus at. A is the constant acceleration, t is the time, and v naught is the initial velocity of the particle. And notice that you can also find the instantaneous acceleration from here. So that is just given by the time derivative of the velocity. So if you take the time derivative of this equation, dv over dt, you see that you get a on the right hand side. And because a is constant, this is actually a constant equation, but calculus actually also gives you this. Now let us go to the another equation, the equation that describes the position of the particle as a function of time. And now we work with the definition of average velocity. Suppose the particle had some initial position x naught at time t equal to 0, and the particle traveled for a time t and went to a position x. Then the average velocity is defined as x minus x naught over t, the change in position over time. And now we can rearrange this equation to write an expression for x in terms of all the other variables as can be seen here. And now we need to know an expression for average velocity, and the average velocity is just the initial plus final velocity divided by 2. It's an average of a quantity, right? The quantity at some initial point and the quantity at some final point, and if you divide by 2, you get the average of that quantity. So v average is written as half times v naught plus v. And then let us, instead of v, we substitute the other equation, v equals v naught plus at. And for average velocity, we get this expression, v naught plus half at. And then we substitute this expression for v average in the equation for x, that is in the first line. And we get this equation for position as a function of time that we saw a few slides ago. So this equation gives you the position of a particle if the particle was at some initial position x naught, traveling with some initial velocity v naught, and had some constant acceleration a. And notice that this equation is a parabola in time, because and this is a special case because we assume the acceleration is constant. Again, if you take the second derivative of this equation, you will get the constant acceleration back, basically. So just a recap of this equation, these are three important equations that are used to solve various problems in physics. The assumption behind these equations is that the acceleration is constant. And in problems, you will be given some of these variables and you will be asked to find something else. And you have to be clever about which equation to pick to solve the problem. If you pick the right equation, you can solve the problem much faster. So let us now look at a special case of motion under constant acceleration. And this is the example of falling objects under gravity, basically. So if I let this object fall, it falls under the force of gravity. And this is also a case of constant acceleration. The acceleration in this case is given by minus g, because the acceleration is pointing downwards. There is a negative sign. G is the acceleration due to gravity, which has the value of 9.8 meter per second square near the Earth's surface. So then we can apply the equations that we have just derived, but substitute minus g in place of a in those equations. And we can analyze motion of freely falling objects. And notice that in some in this type of problems, we will make an important assumption. We will, for the time being, we will ignore air resistance, because when air resistance is present, the acceleration is actually not constant. So these equations cannot be applied in that case. So we will assume that air resistance is 0 and apply the equations of motion to freely falling objects. So this is an worked example. Let us go through this in more detail. So the problem states a ball of mass 10 kg is dropped from a height of 20 meter. What is the final velocity of the ball before hitting the ground? So we are given the displacement from an initial height to a final height. We are not given anything about time. We are asked to find the final velocity. So let us use this equation that we showed. V square equals V naught square plus 2a y minus y naught. Y minus y naught is that displacement from some initial position to some final position. And let us see what variables are given in the problem. So y minus y1, the particle was at some initial height, and then it fell to some other final height. So the displacement is actually negative in the vertically downward direction, and the magnitude of this displacement is given as 20 meter. So y minus y naught is equal to minus 20 meter. And this is a case of a freely falling object. So the acceleration is a equals minus g, and the object is starting from rest, right? So its initial velocity is 0, and we have to find what is its final velocity before it hits the ground. So let us plug in these numbers in this equation, and then we can obtain the magnitude of the velocity. And after plugging in all the numbers, we see that the velocity comes out to be 19.8 meter per second, and the velocity is actually pointing vertically downward towards the ground. Now let us go to the second special case that we will analyze. This is a case of 2D motion. We call it projectile motion. So this is there are many examples in nature. For example, if you are kicking a football at some angle above the ground, then the motion of the ball can be analyzed by this case, the projectile motion. If you are throwing a basketball into the hoop, then that is also a case of projectile motion. A cannon firing a cannonball, that can also be analyzed by this case of projectile motion. And over here in this plot, the position of the xy position of a particle undergoing projectile motion is shown, and the velocities are shown at each point along the path. Notice that the path looks like an inverted parabola. There are some important points that you should note for analyzing projectile motion. So there are two dimensions involved, x and y, and we need to analyze these two dimensions separately. So, and in the vertical direction, when the object is moving, the vertical direction is just a case of motion under the force of gravity. That means it is just under the acceleration due to gravity minus g. So the vertical motion can just be analyzed by the equations of motion we have derived. But if you substitute a equals minus g, and g in this case, as we have described, is 9.8 meter per second square. Horizontally, there is actually we will assume that there is no acceleration. The particle is traveling at constant velocity. So the horizontal acceleration a equal to 0. And we will also ignore air resistance in this case. Otherwise, we won't be able to apply the equations of motion. Then we look at the two dimensions separately. This slide shows you the equations for the two directions of motion, horizontal motion and vertical motion. Both directions obey the equations of motions we derived for constant acceleration. But in the horizontal case, you have to set a to be 0, because we assume there is no acceleration in the horizontal direction. In the case of vertical motion, the acceleration a equals minus g, because this is acceleration due to gravity. The particle is moving vertically under the force of gravity. So in the vertical direction, we can also apply the equations of motion, constant acceleration, but instead of a, we have to write g. Now let us work on a problem on projectile motion that will make things clearer. Problem is showing a projectile being launched at 10 meter per second velocity, acting at an angle 30 degree to the horizontal. So we are in the first part of the problem, we are asked to find the maximum height reached by the object. And so for the maximum height, we can just analyze the vertical motion of the projectile. We don't have to analyze the horizontal motion. And notice the vertical motion is under acceleration due to gravity, which is a constant. So in the equations of motion, we have to plug in a equals minus g. But we also need to know the initial component of the velocity acting in the y direction. And we can easily find that by using vectors, by resolving the velocity vector into its x and y components. So for the y component, we get 10 times sine of 30 degree, which comes out to be 5 meters per second. And when the maximum height is reached, the object is also at rest because it's traveled all the way up and then it slowed down and came at rest before it reversed its direction of motion and began to fall downwards again. So the final velocity when the maximum height is reached is v equal to 0. And then we can just apply this equation, v square equals v naught square minus 2gh. Notice that we have used a equals minus 2g. And we have to find h, the maximum height reached. So we know the initial velocity in the y direction and we know the magnitude of g also. So we get the final height as 1.27 meter. And then for the next part of the question, which asks us about what is the total time of flight, we have to use this second equation, y minus y naught equals v naught yt minus half gt square. And we can find the time of flight when the y height, when the distance traveled in the vertical direction is actually 0. So, and there are two instances when that happens. Initially, just at the instant when the projectile is launched, its y displacement is 0, right? Because it's at ground level. And then its y displacement is 0 again when it has reached its final destination, that is, it has fallen to the ground. So if we can find the time from this equation, the time when the object has fallen to the ground, then that is the time that the problem is asking for. So then we set y minus y naught equal to 0 in this equation. We know v naught y because that is the initial vertical component of the velocity. So we get a quadratic equation in t that is 0 on the left hand side, and then we can solve this. It has two solutions. It gives a solution of t equal to 0, that is the initial instant when the object is launched. So that is not the case we are interested in. And the other solution of the quadratic equation gives us 2 times v naught y over g. And this is the time of flight. If we plug in the numbers, we get something like 2.04 seconds.